Okay, welcome everyone to this week's compiler architecture meeting. This week we've got a number of items on the agenda. To lead us off is Yan Luo, who'll be talking about a proposal for concurrent scavenge read-berry patching. So I'll turn it over to Yan.
Sure. So I'm here to basically make a case for concurrent scavenge read-berry patching framework that we are trying to design and implement. How much detail do you think I should go into for CS?
Whatever you think you need in order to be able to justify your design.
So for CS, we already have a working implementation where the scavenge of GC happens concurrently with the application thread. So the idea here is to, instead of having a big pause where we do GC, where we do all the tracing and copy, the idea is to amortize the effort and spread them out into the application threads while they're running. So we eliminate the pause, and at the same time, we have some background threads that helping out the application threads, picking up their any slack that they have left for GC. So in order for the Java threads to perform the GC work previously, we enforce a rule where whenever a Java application thread trying to load a reference field from an object on heap, we will implement a sequence of instructions called read-berry, where we will try to garbage collect the referenced object, i.e. the fields that the object the fields point to. So we will perform some range check in our compiled code, and if the range check succeeds, it will basically perform a call to the GC where the referenced object will be garbage collected or copied into the appropriate place on heap. So currently, the instruction that we generate in the main line of JIT code consists of a variant of a load of the referenced field, and then a compare with basically a range check, a series of compare instructions where we compare with the heap base and the heap top. And if the address falls within this range, we basically fall through to the next bytecode. And if it fails that range check, it will basically call out of line to the GC code to do the collection. So we want to make it faster. So one way to make it faster is we're thinking of basically patching out this piece of code, which is all over the generated code cache, by replacing them with no ops.
So you're talking about replacing multiple instructions or one instruction?
I'll get into that later. So overall, the idea is somehow replacing them. Whatever they have in the main line, we replace them with no ops.
And the reason you want to make them faster is because you perceived and measured a performance bottleneck?
We have some data that sort of support our case. One piece of data is in the runs, the JVB runs that we conducted, we measured how long the application is under the CS mode and how long the application is not in the CS mode. So we found out the CS mode, meaning the starting from the GC start pause to the end of GC end pause. So basically, a GC cycle, the duration of a CS cycle. And
just to be clear, that's the period of time where the range checks are actually doing useful work.
Yes.
So those comparisons with the heap base are doing useful work during this window where CS is active, right? Just to be clear on that point.
Yeah. So the duration where the range check instruction is actually useful versus the duration where range check is actually not useful. The measurement we did on X and on Z point out to a duty cycle for the instruction where the range check instruction was useful was only 10% of the overall time. So 10% of the time the range check instruction are useful, and 90% of the time we're not under any CS mode, i.e. they're not useful. We will continue to execute the range check. They will always succeed, fall through. And so that's one piece of data that supports that, okay, we are trying to optimize for a 90% scenario if we can somehow, get rid of the cost of the extra path length and the extra code cache waste for 90% time. That should give us the, handsome win, we hope. The other piece of data is within the 10% of the time when the range check instructions are useful, we do the range check. If the range check fails, we call out to the GC. So only 10% of that 10% of the time, we actually needed to call out to the GC. So that really tells us, these two pieces of data, that really tells us, the cost of the time when we spend actually when the GC is active are actually not very, very high. So that sort of reinforces our conviction that we should be doing something where the CS is not active, where 90% of the time is.
I think there was another data point that's worth bringing up, right, which was so if you take a garbage collector that doesn't require these range checks,
Yep.
and you forcibly insert them, right,
Yep.
so that they will always succeed and fall through, you never have to call out. The throughput penalty of just spraying those checks into the generated code on x86, I believe you said was on the order of about 5 or 6%.
Yeah, actually, yeah. So the delta with our current CS implementation and GenCon is around 10% on the three platforms. And we did experiments where we just take GenCon, regular GenCon, and we try to emulate the effect of CS by just spraying those instructions in, but they just never do anything. They just cause the extra path length and the extra cache. So just by doing that, we were able to regress. So most of the 10% regression, we were able to reproduce that. So close to 7 to 8% regression, we were able to reproduce that just by, adding those into the regular GenCon sequence. So that's really, another piece of data that points to, just by doing this useless check, we are able to slow down quite a bit. So hence, 90% of the time, we are not really doing much of anything useful.
Do you know how much, so assuming you were patching these to knobs, do you know how much of the regression is attributed just to the extra iCache that you're taking? So rather than inserting the actual instructions, what happens when you insert knobs? Do you get the same regression, or?
No, so the knobs on x86 were, I believe, in the noise margin of the measurement. So it was sub 1% when it was measured by Victor previously. So he'd done an implementation where there was a single knob in the code where the checks the check would be, and with that one knob, it was in the noise margin. That you couldn't detect the knob essentially.
So in other words, it's actually not the code cache; it's the path length.
It's the path length. So I think that there are two problems, right? One problem is that the heap base has to be loaded. If the heap size is not fixed, you have to load the heap base from somewhere. There's an overhead for that. If it is fixed, there's still a conditional branch that will, the processor can continue speculative execution, but there are limits on what the processor can do while in that speculative execution mode because of that conditional branch. And that conditional, the speculation is a big part of that overhead. If you turn that into a knob, that saves you significant amount of time because it essentially disappears during instruction decode and dispatch rather than actually needing to enter the pipeline and potentially hold up the completion of subsequent instructions. So there's a data point on that that says just spraying a NOP in the required places does not add a significant throughput penalty on x86. That experiment I don't believe is being done anywhere else. Sorry, Ian. I thought that was an important point of discussion.
It's all good stuff supporting our case. So that's the piece of data that we try to rely on in making our design decisions. So we sort of came up with the idea of basically our strategy is amortization again. So we don't want to, because we know there are so many loads all over the code cache, we do not want to patch them all at once within one huge pause. That would just basically kill our response time. So we want to do it lazily and want to amortize the cost. We try to achieve that by utilizing our the existing GC pause mechanism. So we have a start pause where the whole application stops and the GC takes over to mark the start of a concurrent scavenge cycle. At that time, the GC will walk every Java thread stack frames and then basically records all the collected reference on stack and mark them as the root set to commence the tracing of the object reference tree. And because there's an existing mechanism to do the stack walk, we want to, while the GC threads are doing the stack walk for every JIT frame that it visits, we want to patch that method body right there at the CS start pause. So that's one piece. So when the pause ends, all the Java threads will pick up resuming execution again, and it will be patched to the correct sequence where the range check is actually there. So those methods can continue to run functionally. And what about all the other methods? So that's where the lazy patching comes in. So we want to patch those methods that we didn't execute during GC pause, GC start pause, but we're going to execute after GC pause time. Those methods will be patched by itself upon method entry. So what we came up with was a sort of a small snippet of code at method prologue where we will check the state of the method. And then if the state, I'll explain that in a minute. If the state of method doesn't match with a global state, it will basically call out to some JIT helper that will basically patch the entire method body. So what is the state of a method? As far as concurrent scavenge is concerned, a state of a method can be in one of two states, either patched or unpatched. Unpatched meaning, we have the range check instructions in there for every load that's reference load. And patched, meaning, those range check instructions are replaced with no ops. So at any given time, a method body can only be in one of these two states. So having that notion, then we look at what the global state means. A global state is when the GC signals the JVM saying I'm going to be in the CS active period, or I'm in the CS inactive period, where 90% of the time is. So basically, when you have a GC start pause, the GC will set up some variable, some global variable saying I'm in CS active, and then it will start running concurrently and until the GC end pause, where the global state will be flipped to CS inactive. So now you have a method state and you have a global state. A method state, if it's patched, matches the CS inactive state. So if it's CS is inactive, I don't care. I can just run a no-op instruction in lieu of the rebarrier. So they match. And the unpatched state matches the CS active state. So at any given time, a method can be in one of the two states. And at any given time, on the other hand, at any given time, a JVM can only be in one of CS active or inactive state. So with that, when we enter the method prologue, we check the method state to see if it matches the global state. If they match, that means the method, the instruction, the rebarrier instruction is in the correct state. I can just run it without patching.
You do that before or after the Stack Overflow check?
That should be before, I believe. Yeah. Yeah, we do it before.
Is this a separate check then? Like, so can you not combine it with the Stack Overflow check, as in?
Right now, the way I design it right now, it's a separate check, but I can certainly look into the details of stack check to see if I can combine them.
Yeah, not even in CS mode, for example, or in that phase. Maybe you just start checking the Stack Overflow check, you would find that nothing needs to be done whatsoever.
So I think one of the things that Jan was aiming for with this was the simplicity of the check. So checking the GC state or other things like that will necessarily require you to interrogate some part of the runtime system. But the statement that's being made here is that there is a state that the JIT believes that the methods need to be in. Either they need to have the read barriers running or not. And if you use a bit in a control word that's stored globally that says we need them or we don't need them, then checking the state of the method is to check the method body's control word against the global control word, which it can be two loads, one of which can be done very easily because it can be right near the method body, and one will be global. And you can do a simple bit XOR to see if you need to worry about this. Now, the use case here is for CS, but the hope is to use it for other things. I have designs on trying to use lazy patching to allow us to turn patching on to patch in profiling code, software profiling in method bodies. So again, there you would want to have a state that, yes, we want to turn profiling on. We'll profile any method that runs or some subset of methods that run, and we want that state to be toggled on or off in a similar way to what we are proposing for CS. So having a general mechanism where you're just going to load a control word and compare it against the method state, yeah, you have an extra load, but you have a lot of flexibility in having multiple different features enabled or disabled and calling out if the body does not match the state that you expect.
So overload the Stack Overflow check.
Overflow check did not fail because of this extra reason if CS is not active, then 90% of the time you're not doing any work that you weren't already doing. You're just doing the same check you were doing before. It's not going to fire. You're not going to go out of line. More cost if it does fail in that 10% of the time, which is why I wanted to put it out there as something to think about, whether it somehow works out to be a net positive if you think about the sequences carefully enough. I'm not saying it is the right answer. I'm saying it should be considered.
I think it's certainly worth considering.
So where is the global state? You're getting that off of from a Java perspective. You're getting that off the VM thread. Is that where you're getting it, or what are you checking?
It can be VM thread. It can be VM thread or
what were you thinking though? How did you design it? Was it
I was thinking
global somewhere, like a static that you're checking?
No, it's probably VM thread. VM thread will be easier to get to condense the sequence. Otherwise, you would have more instruction just to grab it.
If it's an absolute address, though, you can just hard code the address and load from the address.
If your goal is less code, then don't do that. On Power, that's going to give you.
Don't do what? The VM thread?
Absolute address.
Don't do absolute address.
It takes 5 instructions to materialize on Power, is what you're
Right.
saying.
Well, we can put in the talk.
Yeah.
In talk.
But then you pay a load.
Yeah.
Use an extra load to get the address.
Load is okay, but the talk is limited.
Okay.
After you run out of talk, your problem returns.
But that's a global value. It's not specific per thread. It's specific.
No, but it could be stored per thread if you update all the threads while you're stopped.
Right.
Easier to load from the
GC
thread.
is
You
going
can store n copies of it.
Because the GC is going to upload the certain values in the thread already for CS. Because you have all those base and top and compressed base and compressed top.
Yeah, that's true. Yeah.
It's already doing that.
We can have a control word there if we want.
I think from what I'm hearing is two things. One is the mechanism of invoking the feature, and one is the feature itself.
Yeah.
It seems to me from the OMR perspective, at least, the feature is being able to patch instructions and revert them back, something we currently do not support, where the mechanism of invoking that logic is OpenJ9 specific. So I think we should design this as the feature itself, which is patching and unpatching instructions, and the mechanism to invoke it is something totally separate.
OMR may wish to give some consideration to it, because if OMR is going to have a notion of software profiling, which I certainly hope will be the case in the not distant future, there's some persistent method information infrastructure that needs to be promoted into OMR before we can do that. But we have software profiling techniques that are very low overhead that we've developed in the context of OpenJ9 that are not Java specific. And being able to toggle that profiling on and off, at least with some default generic implementation in OMR, would certainly be useful for OMR languages if you could get profiling data just from having implemented the method. But I do agree that there are two concerns to that. And
there is an OMR VM, but yes, there is. So essentially the field is looking at could be put there.
Yep.
And then maybe that makes it less J9.
Yeah.
If it's just a heat base and then size of the heat.
Yeah, well, the actual content of the range check will be J9 specific, right? It's the notion that I have a chunk of code that I wish to run some small proportion of the time, and I wish to have reversible patching to get to that chunk of code and back again, or patch that.
Right. The infrastructure should be in OMR, but the mechanism may be OpenJ9 specific to a certain extent, at least for CS. Of course, it can be general.
Yeah, I think it depends on what design we settle on, I think, for the control mechanism. If it ends up, conflated with the Stack Overflow check and whatever happens in there in OpenJ9, then that may be the way that OpenJ9 wants to do it. You may wish also to have a more generic implementation in OMR so that it's kind of supported out of the box, but maybe not as efficiently as if you carefully conflate it with your language's Stack Overflow check or whatever other things you do on method entry, right? You could certainly even have the OMR VM thread with the control word, with an explicit control word check as the default, and you can replace that in the downstream project with something smarter.
Yep. I mean, the infrastructure is you call a method in OMR which patches an entire JIT body.
Yep.
And the mechanism you invoke that may be specific.
Yeah, and there'll be hooks for the different kinds of things that need to be done.
So you mentioned, so you're going to patch multiple instructions. Do we have concerns for atomicity?
That's under discussion. We have options to, we don't want to do too many. So I'll just talk about currently what we have. Currently on X, we have a load and then a compare, and then a jump. Basically a compare and a jump to the outline sequence while we do the rest of the rebarrier. So that's 2 instructions at minimum we need to patch currently on x86. On Z, all the rebarrier sequences in the main line, so there's like 7 or 8 or something. We don't want to patch that many, so at least some of them needs to be outlined. But going back to the X, so we have 2. We could patch 2. We'll patch 2, provided that for each instruction we patch, it's atomic. The reason why I think it's functionally correct is it's basically patching the compare and the jump. We patch the jump, we just do the compare. I don't think it matters. It's a way to compare, and then we patch the next.
So before we get lost in that particular detail, there was one thing that we were discussing, which I think is important in considering the multiple instruction patching notion, right? So on a platform like x86, where the memory model has strong consistent guarantees, right? Strong ordering guarantees. If we have it so that every thread, every method when it enters checks the state of the method to see if it needs patching, whether that's in the Stack Overflow sequence or in the main part of the prologue, one or the other. You're going to run this check. You then are going to run patching code that's going to go and patch the instructions to a fixed sequence that's going to be whatever that site is going to be. And that thread will then mark the control word as having been updated, right? Update the state of the method. Basically, it's patched to this configuration, and then it will begin execution. So on x86, where you have ordering guarantees, if all threads are checking that control word, right, and the last thing that you write is the method's control word update, multiple threads could enter there, and as long as the patching is sort of idempotent in that it will always do the same thing, then if multiple threads come in and multiple threads go and patch, they're all going to patch it to the same thing, and execution can continue. So whether you're patching one instruction or multiple instructions, no thread is going to enter the method until all the patches have been written.
Right, but then we're shoehorning ourselves into always executing the patching logic on the execution path. For example, you can't have a background thread which does the patching.
Right. So so if you certainly, if you're going to do the check in the main line, and if you're going to do the check on entry and patch on entry, yes, then you're going to rely on multiple threads, going out to the patching logic so that you don't have to worry about aligning absolutely everything.
It also means you would need some sort of mechanism to patch methods which are currently executing within the same body. So you would need an async check type thing.
Isn't that what the stack walk is doing?
Yeah, so there's a stop at the moment.
We have a stack walker in OMR.
Well, I mean, no, but I meant that he described 2 mechanisms, and you need both of them, right?
Right.
The entry gets the methods that are.
There is a chance that at GC end, a thread could be within the body while it's paused, and then it could be running while somebody else is patching this thread.
Right.
At GC end.
Right, but so at GCN, somebody's going to yield, and somebody could still be running and patching the method, and then yield.
Right, no.
You could be executing within the method while another thread gets in the patching logic of the entry.
Right.
and you could potentially overwrite instructions which another thread is currently executing.
Right, because the GCN...
Before you ever reach a GC point.
Yeah, GCN, I don't think there's a stack walk. So we don't... Only the stack walker patching applies to GC start. At GC end, we don't... I don't think we do that.
Right. If we were to walk the stack at GC end,
yeah,
then we could patch the bodies that are on the stack at that time, and then there would be no concurrency issue there. But if we don't, then we do have to care about the code being
Alex, are you online?
No.
Are you on the phone?
No, Alex isn't. But I think that, like, whether you're going to patch one instruction or multiple instructions is a function of how when your patching is going to, like, the atomicity concern is a function of what it is that you're actually doing and when you're planning on doing it. The infrastructure doesn't necessarily have to concern itself with whether you're going to do one or n. Now, if you're going to do n and you're going to do it while the program is running, then you better make sure that you align it and whatever according to the requirements of that platform.
Okay.
It's also possible that you can factor the current read barrier code to not require multiple instructions. So for example, on x86, I know that when Victor was working on this, we did an experiment where we moved all of the read barrier checks out of line, both of the range checks out of line, and did a call and a return. And on x86, because of the call return prediction, that actually didn't add it was unmeasurable, the extra overhead of doing that, and meant that we only had to patch one instruction, so we didn't even have this problem, right? It's a call to an address that's an out-of-line code sequence, and then it wasn't a problem. Now, on some platforms, a call and return is no good. You know, your jump might be better. But again, we're coming down into the specifics of what it is that you're actually going to patch, and I don't think that the mechanism necessarily needs to be that specific.
I just wanted to make sure it's a design point that patching is potentially non-atomic.
Yeah.
Mm-hmm. Yeah. But I think it comes down to the utilization of the infrastructure that requires that particular bit of care, right?
That's fair. I mean,
yeah,
it's fair to design it that way.
I think it provides OMR with the most flexibility in how to use it, right? Consumers of it.
The thing is, I don't think you can't do multiple instruction patching on some platforms without having synchronization in the instruction path. So you can,
yep,
and that makes it essentially impossible to do this. You will never break it even.
Right.
Because you're going to have asyncs in there to stop the processor to make sure that they don't execute instructions in the wrong order, even though you patched in the right order.
Right.
So I guess what I'm saying is that I don't see how you could do that.
Can we do it at the end of the patching helper? We do a sync?
Yeah.
No. It doesn't matter what you do on the writing side, on the patching side. The processor that's potentially executing those instructions can see them in any order.
Right, but they all have to go through the...
Well, so in the case,
prologue, right?
Well, right, but in the case where you're dealing with the C at the end, we were talking about. So we were talking about the cycle is ending, right? And you can have you're not going to walk the stack at that point. Somebody can enter the method and patch the stuff out at that point.
But you're not gonna, yeah. Well, you're already in there, so you can't. For that one, you can't, yeah.
Right. However, one question for you, Eunice, then is, say on power, if we have an inline, if we have the sequence as a load and then a compare and a branch conditional. Let's say we leave the load and compare on power as they are, and all we're going to patch out is maybe the branch conditional. Now, whether that's performant or not, I'm not going to argue about that right now. But if all you were going to do is patch out the branch conditional, right, and you could run the NOP or you could run the branch, it doesn't matter because the branch will fall through, the condition check is okay, then as long as the write is the single instruction, you either see the new version or you don't, and then you don't need the IC.
And even if you see the wrong version for GC end, it's functionally correct.
Right, like the load and the compare will generate a valid result. That will
in the worst
result
case,
in the
you just
conditional
run the range check.
You're patching one instruction, you're fine.
Yep.
Two or more is very dicey.
Right.
I think 2 or more is okay at GC end. as long as per instruction is atomic.
Possibly. I didn't quite understand everything.
Well, I think it's going to require some careful thought based on the memory models of the various platforms and the allowable patching as to what is the sequence that you actually want to patch in or out. On x86, we have a little bit more flexibility in the patching than on, say, Power, and we may choose to patch a couple of instructions, but at the very worst, there's kind of a one instruction patch that gets us most of the performance that we want, which is that kind of call return style. Now, that may not work on other platforms. We'll have to study the sequence in the context of the platforms. The architecture may not make it possible to regain as much of the performance as we can on x86. But we'd like to put the tool into OMR to let us try and do the x86. And if it helps the other platforms, then fantastic. That's kind of the argument that I think is being made here. And Philip is completely correct. There is a concern about the atomicity, but I think that comes down to the design of the patching that uses the infrastructure.
Fair enough. Yep.
And some afterthoughts. Basically, the something that Philip mentioned in the issue was how long it takes to actually do the patching. Was it too expensive, considering how many indirect loads are there in the co-cache? We could do something like only doing patching for loads that are in hot blocks. That could cut down, we hope, a good number of useless patches sites.
But again, that's orthogonal to the infrastructure that OMR would need to support doing the patching. It's a choice of where do you employ the patching, right? And
yep.
One design point would be if the patching takes too long for the use case you're looking at, you cut down the number of places by sacrificing performance in places that you don't expect it to run very often, and you just leave the code in the patch state or whatever, right? But it's a choice on the correctness and the particular thing that you're doing as to whether that's acceptable or not.
So presumably you need to store this in JIT persistent memory, right?
Yeah, well, I think it would probably end up looking like a runtime assumption kind of thing, which is not being factored up into OMR, but like there is a runtime assumption table, and the abstract sort of runtime assumption exists in OMR. The concrete runtime assumptions that are currently used are down in OpenJ9, but the notion that you have a location, you need to keep track of these things against a certain kind of operation. The major difference from the current runtime assumption design is that the current ones are one way.
Right. So you don't need to store what you're patching over, whereas
right.
Now you would.
Now you would.
So do you have any estimate of how much footprint that would incur?
No, not at the present time.
I know Marius was concerned previously about the size of these tables and the metadata that we store.
Yes, and that's certainly very true for when you're like adding a pointer to every single one of them when you can achieve it without doing that. This one would require a reversal. There is a payload slot available. Not all of them are currently using it. So we may be able to hijack that with a union. We'll have to have a look because it's not currently factored up into OMR, so how it would look.
I think the bigger concern would be the bytes you would have to effectively store the instructions you're patching over.
Yes, and I don't think there's any way around it for reversible patching.
Yeah.
Well, depending on what you're patching, if you make sure that what you're patching is, we're going to replace this jump with a fixed offset to enough, then you could get away with storing just the offset, which could be smaller than...
Potentially smaller.
Right, but then you can't patch compares. Can't patch compares.
Right.
Yeah. I mean, to have a general infrastructure, then yes, you have to store the bytes that you're overwriting.
Yeah.
I don't think there's any way around that. It's a footprint cost of doing reversible patching.
Kind of like a debugger, right? You put the debug break instruction there, and you remember what's supposed to be there, and you pretend that's what's there all the time.
Exactly.
Yeah. And yeah, it'll have a footprint cost, but there will be a throughput gain, but it's a balancing act. I think that might be a trade-off that would be acceptable in the OpenJ.
Yeah, we can check how much it actually ends up being as well.
Yeah. And again, the same idea of reducing the amount of patching time, you can also reduce the footprint by ignoring the ones in low frequency blocks.
So we can have a lever or scale, I guess.
Yeah, it's a spectrum.
Yeah.
It's a spectrum.
Yep.
It's a tool. You choose to use it where it makes sense to do so. If you overuse the tool, then you pay the cost.
So as part of this effort, will we be syncing some of the runtime assumption table code from OpenJ9 down into OMR, or?
I'm not quite sure.
plan?
I'm not quite sure how that's going to look. I think we'll have to actually do the engineering and then try to figure out what makes sense to factor. The API for the runtime assumption table is in OMR. The guts of the implementation are not, and most of the guts of the implementation right now are too Java specific to really be useful. So whether it's that we contribute the runtime assumption implementation that allows you to store this stuff, and OpenJ9 does a way of storing them, and we have some much more naive way of doing it in OMR as a placeholder for the time being, pending the rest of that stuff being refactored or something, because I think refactoring that runtime assumption table is kind of beyond the scope of what we're proposing here. We just want to...
Okay, yep, that's fair enough.
Any other concerns? Questions?
Have you implemented any of this yet, or is this just all theoretical?
We are going to pretty soon, right? We are trying to sort of compartmentalize certain chunks of work, and then we'll have a
few people working on it.
Yeah.
So have we built the infrastructure? No. Have we done the experiments that suggest that we will get performance from it? Yes, but we haven't built it yet.
So just looking at your x86 code here, if you're using RIP relevant addressing here, you're assuming this is only 64-bit?
Well, you can achieve you can do a similar effect with a pop and a push and a You can generate a RIP relative address on 32-bit with a small instruction sequence, but it doesn't have to be RIP relative. If you're going to store the word in the control word in the prologue, that's one way of accessing it. On 64-bit, it's highly efficient. On 32-bit, you might want to do something else.
I mean, on 32-bit, you can just put an entire address into a memory reference.
Yeah.
So.
Your relocation on it, too.
Yep.
It's your...
Yeah.
But it's just a relocation. We know how to relocate addresses already. We can relocate the method entry. So.
Yeah, we have relocation records already for addresses that are effectively within the JIT code or at a fixed offset from the JIT code. And we use those for table switch at least.
Yep. Well, this could be another one of those if you wished.
So, one of the things that was mentioned before was that the call return scheme that you tried earlier didn't have much of an overhead at all, right?
Yes.
Okay, so if you, let's say, did a call return scheme first, and then as the second step, you patched all the methods. So every method only has one call return to the sequence that does whatever needs to be done and then returns. And you just did all methods because there's only a few thousand methods. Every single one only has one call and one return.
You need a call at every read barrier site, so there are N calls that have to be patched per body.
Okay.
Right. So at the moment, the read barrier sequence is specific to the read barrier because it will use the registers.
Sorry, but the overhead of doing the call and the return was negligible, you were saying, right?
Yeah, so if we outline, so at the moment there's an outline sequence which consists of a range check and then a potential call to the garbage collector, a load and then a return and then a jump back. And in the main line there's a load, a compare, and a jump conditional. We move that first load, compare, and jump conditional, so there's two range checks that have to be done. Keep base, like collected region base and collected region top. So we moved that first range check that was inline into the top of the out of line sequence. and we had one sequence for each read barrier. We didn't deduplicate them. It was one for each, and we did a call to the sequence for that particular read barrier with a ret back to the main line.
But those different call types could have been deduplicated, or?
It would complicate doing the out-of-line sequence because the out-of-line sequence relies on the registers that are live at that read barrier. So where you're going to get the reference from could be R8 or RAX or whatever. The one that we generate is specific to the site. Now, we could do a form of deduplication, but that wasn't done. We were already generating one of these stubs for every read barrier. We just kept doing that. We just moved the main line out.
Okay, so I guess I'll modify the original comment slightly then and say, yes, you can either coerce the object to be in the same register so that you can literally have one sequence,
yep.
Or you can have n sequences where n isn't a huge number because there are only so many registers that the object happens to be sitting in the method. N times the number of methods may not be such a drastically large number of sites. So
the deduplication is only saving footprint for the actual instructions that are going to run for the read barriers. The number of sites that need to patch remains unchanged because you must patch each read barrier site to call that sequence. So the number of sites that need to patch are the number of read barrier opcodes.
It's the mainline part of the code that we need.
The mainline part of the code that's patching.
For the call is. You're patching the call, not the...
Right, but I thought the call and the return were not significant overhead. So I don't care about patching the call. What is significant overhead is the checks, isn't it? That was what was said earlier.
I see. So Vijay is suggesting going into the sequence that you call and just putting a return at the beginning of it.
Well, based on the assumption that the call return isn't that expensive and there aren't that many sites if you did that.
It's another design point. You would need the same infrastructure kind of regardless.
Yeah. Again,
right, you'd have to know what was there. So
but the mechanism of patching, you would still need a patching infrastructure there.
But one instruction. I have a slightly different question. So if you're
Sorry, you have a patching infrastructure today.
You need a reversible patching infrastructure.
Yes, but not a just-in-time reversible patching infrastructure.
I would still worry that with a large number of compiled methods, you could still have a problem where the amount of time that it takes to patch all of these is non-trivial.
It's possible.
And the fact that there are other potential uses for it, such as software profiling, I don't know that the small extra engineering cost, small week or whatever, of making sure that we can support the more general case, I don't know is misspent. It provides a utility in OMR that could be very useful for a number of things. There have been discussions about other kinds of reversible patching at certain points in time.
Sorry, the reversible patching is not in question. Right? Obviously, you have to reverse it.
Yeah.
It's the just-in-time aspect of it that was at the heart of my question.
Yeah. I still worry that writing that many instructions across all the methods in the code cache could still add up, would be my concern. Because we're talking about a very short pause. What we're trying, people are actively moving path length out of that pause to make it shorter and shorter.
Yeah.
Putting path length into it is...
Should we maybe try to estimate?
Yeah, we can...
What kind of order of magnitude of time it might take in a reasonable scenario?
Well, how long does it take to patch 100,000 things?
Right.
You can even hack the GC, like the stop the world CS cycle when it begins. We stop the world on every thread. You can traverse all the methods and just patch it right in the C code.
Yeah. But yeah, we should do that. But I agree with what Andrew's saying because CS is we don't want to spend all the time doing all the CS work to bring us where we are and then shoot ourselves in the foot by putting by increasing back the GC pause time at the start. Because if we take the just-in-time aspect out of it, we might have to increase the start pause to a point of not being very acceptable.
Right. My point was more just that it might help support your case better if you had like a back of the envelope calculation.
That I agree.
That there's, you know, if we have 10,000 methods with this many read barriers on average, and every time we touch one, we miscache, how much time does that take, right? And then to have some idea of that would...
Right.
Yeah, that would probably be enough to satisfy me having some idea of it.
I think an easy way would be just to put a debug counter and right before you call out to the GC read barrier, just count how many methods you're actually seeing during a CS cycle. If say you have to patch 10,000 methods, whereas you're only executing 100, the just-in-time would only patch 100 methods, whereas the non would patch 10x more, 100x more.
I think counting the number of methods like that is cheap. Trying to estimate the amount of time it's going to take to patch n sites, that's much harder to simulate because we don't have any of this infrastructure. So you have to write some of it at least to.
I think the summary is do some reasonable exercise, not taking too much time, and convince yourself that this is worth it.
Well, I have a slightly related question, which, assuming that the just-in-time patching is warranted, as I understood it, I've been distracted, so maybe I've missed some subtleties here. As I understood it, most of the checks that you're in, like the check that you're inserting for figuring out when you have to patch a method, is at method entry, and you're we talked about overloading possibly the Stack Overflow check. Did you consider just changing all the vtable entries and itable entries for methods to change it to the entry point that would do the patching? Which
Not
would then
everything's
change
called
it back.
virtually.
That will be another
That
patching.
does incur a per method cost, right? So every method...
You have to do that anyway. You have to set a bit anyway.
Well, it's per... you don't have to set a bit for every method. You set a global bit, and the methods, only the methods that run will
Update
notice
their
it,
bit.
right?
So each VM thread has a control word that says, I want the read barriers to run or not. Each method has a state of, my read barriers are on or off. And when you arrive at the method, you check, do I match the thread state? If yes, do nothing. If not, I need to go and call some patching code. So you're only going to update the control word either globally or one per thread. VM thread is convenient for power. And you only have a small n number of those to update.
Yeah, I suppose it's possible that patching every read barrier site, say, is prohibitively expensive at the time at which we're thinking of doing this. But then patching, every prolog is not prohibitively expensive, depending on, what kind of scaling factor you're looking at there. But I'll just, I don't know that there's even a consequence of that we want to consider right now, but I'll just leave it there.
How do you deal with methods that don't get executed in a cycle?
So their control word does not get updated. We update the VM thread to say we toggle it on, so the bit is set. We start running some methods. They check, their bit's not set, they patch themselves. The cycle ends. We turn the control bit off. We then call a method that never patched. Its control word matches the global control word, and it does nothing. So the lazy aspect of this is you literally only patch on the methods that are going to run, and you only patch things out when you're going to use them. Because if the method doesn't run again until the next CS cycle, it doesn't need to unpatch. And in fact, the unpatching can be even more lazy because in this case, it's functionally correct to keep running the check. So we can even defer unpatching it further.
So that I have this picture straight in my head, like what happens for a long-running invocation? So you get in, let's say you patched it to the CS.
Yep.
Now you're in the method, you're executing while CS is enabled for some time. CS ends, you still not left the method.
At the moment, the barriers will be left in.
The barriers will be left in.
Yeah.
Yeah.
But if another thread enters that while the method is running, then
It will patch.
it will reverse the patching while the method is running.
It requires somebody to enter it. Because the issue is that there is no stack walk that happens at the end cycle. And adding one increases the length of the pause. And we could if it becomes a problem.
Is that a mild argument, perhaps, for having a separate thread that was capable of turning through this?
Certainly possible.
So anyway, we're raising design issues here that
Yeah, I think they're very specific to the use cases in this case.
Just in the interest of time and following the agenda, I think maybe just want to cap this in another couple of minutes, and then we move on to the other topics, because I want to give them a little bit of time as well in the half hour that we have left. So I think that in one of the conclusions that I see from this is that we'd like to separate the engineering the mechanism aspect of it from the use aspect of it. So when you're looking at getting them to OMR, think of it that way. And I think thinking about it in the more general sense as well, like not just x86 specific or anything like that, right? Let's try to keep this as common as possible. Okay. Any other sort of comments for Jan? You can always continue to add comments to the.
I have one, but it
sure.
might risk prolonging this discussion. One more seconds to
Is it vitally important to the? I don't want to.
Yeah, I'll do it.
Sure. You will?
I'll talk to him separately.
Yeah. Or put a comment in.
Yeah.
Okay. Okay. All right. Thanks very much, Jan. Okay. Next thing I wanted to move on to was the RISC-V backend implementation in OMR that Boris and Jan have been working on. Boris, are you there? Do you want to talk about what's next with that and what you plan on doing with that?
Yeah, I am here. I think that Jan is here with us as well. Maybe on this first topic, I will pass the mic to Jan because he was recently making the last pieces of progress, so he knows best where we are. Jan?
Okay, so hello everyone.
Hello.
Well, first of all, I would like to say that even though I did the last bit, Boris did the first bit, and they are always, the most difficult ones. But yeah, now, as I said on the general channel, we make it public the first, let's say, version from which we would like to, take it as a start and then continue evolving. Mm-hmm. This version is based on the AR64 port, and yeah, it's far from being complete, but there is quite a few things that already work. So as of today, there are some 33,000 trill tests that are passing, including integer arithmetic, floating point arithmetic, both like a single and double comparison, conditional comparison like this HCMP, greater or equal sort of codes.
Right.
Calls work, so the recursive Fibonacci works. Mandelbrot works, as I said the other day. So it's in quite okay shape.
Okay.
And what we would like now is to start the process of getting this into the OMR repo, if there is an interest and if that's possible. And yeah, talking about this.
Okay. So first of all, I think that's you guys have made some great progress, pretty much more or less on your own. I think that's really great to see, and we really would like to get this contributed. So I think my just given the experience that I had with ARch64, the approach that we took with that was to essentially not drop the entire thing in as one large commit, one large pull request. We did spend some time on individual aspects of the back end so that we could do a much more focused review on the code and find problems that way. So we found that to be fairly effective. So that was sort of the nature of my request yesterday, that if you can, try to break this up into a number of smaller commits of different aspects of this, so that we can do that focused review. Because otherwise, I think that if it's all going to land at once, it's going to take a while to get through everything, and just to make sure that that we do a proper, thorough review of all the different aspects of it. So I'm not sure what your thoughts are on that. I mean, you don't necessarily have to carve up files. I think that you can contribute different files even, right? Like you could do the machine class, for example, the instruction hierarchy, the opcode tables, things like that. You can sort of deliver those in little batches that people can pore over and make sure that they're sound.
Yeah, well, I mean, the structure in terms of files is pretty much similar to the one of AR64, obviously, which is also similar to PowerPC as far as I've seen. However, the commits, and there is a bunch of them, I don't know, maybe 30. The commits are structured like, they show the progress of actually incrementally rewriting and removing the AR64-bit stuff and making it pure RISC-V code. Now, I am not really sure if it, I don't know how we want to break it, right? We can break it by file, but then, we would have a bunch of commits that we would review individually, but none of them would compile until you combine all of them together. If the idea is that we would create a commit that would make the impression that we started from zero, then I would find it quite difficult and really time consuming. That would be a couple months to just take what we have and then start copying, pasting, and then making sure that it compiles and it will make sense. I'm not sure about it.
I think part of the problem we had with ARch was that we hadn't configured builds for that yet.
We had builds from the beginning, actually. We did cross-compile builds. We don't do native, we don't run natively, but we have the cross-compile build.
Right, but we didn't have the trill tests running.
Trill tests were not running. No, they have to be run manually.
Right.
Yes.
So I think the difficulty is going to be, how do you know that any of the review suggestions are not breaking things?
Well, I think that it's going to, so one of the things we're going to have to discuss as well is the infrastructure that's going to be able to build and perhaps even test it, like adding CI tests for this, right? So, and that might get into, do we do cross-compilation to begin with, or do we run this on an emulator? Or do we actually add hardware to a farm somewhere that we can actually do testing with it?
We do, or I do have a CI setup that runs it on the real hardware on the Sci-Fi Unleashed. I did some experiments with cross-compiling on MD64. It does work to some extent, but then there are some places when you build tools that generate something that is in turn then compiled, and because I do have the real hardware, I didn't bother to fix the CMakes and all that to build these TraceGen or things like this, to build them with native compiler and build the rest with the Invercos compiler. But it's certainly doable.
So the CI testing.
Sorry?
I was going to say, the CI testing that you did, was that just on your own personal hardware, or is that on some more public?
On my own personal hardware, yeah.
Okay, so that's sort of the same situation that we have with AArch64, where we can build it sort of publicly, cross-compile it, but right now, because of the lack of availability of AArch64 hardware in the open, which we're working on, we don't actually have a CI test that actually executes the trail testing on AArch64. So I think we're going to be in a similar position with RISC-V in that we could possibly build it, but we can't actually run any tests until we can get some hardware to back it. And I guess the question would be, where do we get that hardware from? Do we actually need real native hardware, or can we run like QEMU or something like that?
Yeah, you can do all this in QEMU. I just do it in real hardware because first of all I have it. Second, it's faster than QEMU. But I don't have that much powerful machine, so I mean, if you have a powerful x86 hardware, then you might be fine. And for CI, whether it built in an hour or hour 20 minutes doesn't make much of a difference.
Okay. Have you used the QEMU for RISC-V? Any comments on how well that works? Is it a reasonable?
Yeah, it works. I actually spent quite a lot of time on preparing a set of scripts that build the whole environment in which me and Boris develop the stuff. And they generate essentially QEMU image, and then you transfer it on a real hardware.
Okay.
So that is, I would say, pretty much straightforward. So, I mean, there are scripts that build the QEMU image, and you just then launch the QEMU, and a part of the real execution machinery behind, there is no difference.
So that could be...
You can set up the CI inside the QEMU. That's fine.
Okay, so that would be an acceptable solution in your mind, at least until we actually figure out the final native solution. Okay.
Yeah. I mean, it might be possible to get the unleashed still. I don't know. Maybe Boris knows.
Well, I believe you can order one.
Yeah, I think so.
I mean, we get ours as sort of a present from Sci-Fi, but that's because we are individual contributors who are just doing this, ourselves.
Right.
And I think if we're talking about getting one for IBM or something like that, they will be, you'll go buy it.
Okay. Okay, I'm not sure what the answer there yet is. It wouldn't be like a system that IBM would necessarily own. It would have to be something that's kind of out in the public space, so that there are public builds can actually run on it. So, but maybe just circling back to the original question about how this is going to land and whether or not it could be broken up. One of the first things that we probably should get set up is some sort of at least a build environment where, at the very least, you just do a cross-compile build of the code, just so that we can see that it actually works. We can work on adding a CI build based on QEMU as well, so that we can run some of the tests. The request to actually break the initial contribution up was more. It was more I'm not going to be too hard on that because I'm just going to say that it may take a little bit longer to review the entire blob and make to make and thoroughly review each of the different sections than it would be if we could land individual parts of it. So if that's acceptable, then that's the way that we could go. Because I also don't want you to spend 2-3 months breaking it up if it's difficult to do, because that would just be the amount of time that we would potentially be spending reviewing it anyways.
Yeah, I'm not even sure if that kind of breaking up makes sense at all. For one reason, what Jan said, that none of those broken up individual commits would even compile, right? And number two is, looking at how the code is structured, that's the structure of how things are built, how things are broken up into files, right? There is the way how the code is organized, and at every particular snapshot of the code, like at each particular commit, there are reasons why code is structured in one way and not in the other way. So in that sense, using basically a history or change management tool in order to express the organization of the system is just really using fundamentally the wrong tool for this. So I just don't understand how this would work even in principle.
Okay, well, why don't you carry on the way you were thinking, and we'll make do with what we get. The other thing that I mentioned yesterday was I think that there is an Eclipse legal process that we're going to have to follow for a contribution of this size as well. You have to, I believe, create something called a committer questionnaire. It's not really that, it's not a terribly onerous process, but what Eclipse really wants to do is to make sure that any large contributions are, are sort of free from any kind of IP concerns and that sort of thing. So they will actually scan the code and do some things like that with it to make sure that it's properly licensed and attributed to a certain author, that kind of thing. So I will certainly help you with that, just to get that through. But because of it's a parallel process, you could actually make your pull request, but we just can't merge it until we just won't merge it until that process is complete.
Yeah, we have to file.
Yeah, I completely understand that. That's fine, and I am ready to go through this process.
Okay. Yeah.
Fine.
No problem. I imagine. Yeah, I would imagine that it's going to be at least a few weeks before we could actually merge this, just because we do want to be spending some time with the code for sure. So.
The CQ of that nature is usually very straightforward, so I wouldn't expect any issues there.
Okay. Yeah.
Unless they dumped a bunch of GPL code in.
Yeah, that's fine. I mean.
Okay.
Fine. No problem.
Okay. All right. So Okay. So I guess you could prepare to make your PR then.
Well, the question is whether you want the PR with these individual commits that shows how it evolved from the HR 64 to RISC-V, or if you want them all squashed into one.
How much detail do you have in all those individual commits? Do you actually have a description of what the different changes were that you made, or is it?
Yeah, it's like this is like this fixes these instructions and fixes these trail tests.
Yeah,
if we're not going to be able to go back, so if there isn't much detail there, and if we're not going to be able to go back and try out different parts, like if I wanted to go back to a certain version of the machine class to see if this certain problem occurred or whatever, I'm not sure if there's value in that. So I guess I would argue for squashing.
Why don't we start out with the commits we can squash before we merge?
Yeah, what I think
the-
I would propose, or one idea that we were discussing with Jan, was that right now there is several branches that this was developed in, and it is kind of pretty clear what merged into what. And finally, like, there were some smaller ones, and they got merged into RISC-V-Devel, and finally that got merged into the main RISC-V branches of this morning. And what I think is that they're about, what, 35, 40 commits now on the way that separates, like, where we started to where we are now. And I think for the actual master branch of OMR, there is too much detail. So we were thinking about squashing that into what initial commit, saying, well, this is our initial contribution into OMR. And then we still keep that in the RISC-V-Devel branch, all of those things. So if somebody wants to see how a particular piece of code got developed through the different, fixing this bug, and oh no, we tried this, but then we scratched it away, and like, for example, we already did half of this process because our original implementation that we first started with was based on PowerPC port, and there are another about 40 commits. But right now on the branch that we have, we don't have any of those experiments, but we just keep them separately, right? They just don't.
Okay, and just to be clear, when you're talking about keeping them on a RISC-V branch, you mean keeping them on a RISC-V branch in your personal repo?
In my clone, yeah, in my fork.
Right.
We will certainly keep them, at least for ourselves. We can deliver you squashed things, and if you for whatever reason want to have more detailed or see the evolution, there will still be something we can point you to and say, look, this is how it developed.
Yeah, because it's all in the open. Like, all of the steps that we did and how, and, to prove for legal, for example, that, yes, we wrote this all ourselves. Here is a detailed history starting from, more than a year ago. And it's.
Yep, sure. Yeah, that sounds good.
But to push 80 commits now into the main line, saying, oh, these were all the steps that got to the RISC-V port. Like, it just clutters.
Okay, so the suggestion that we're going to make is that when you do your first pull request, your initial pull request, you can have all the individual commits there, but when we actually merge it, we're going to ask that you squash them into one. So we see the history of your development on your initial pull request, but before we merge it, we'll get you to squash it into one, and so we have a single.
Just for context, it'll help with the review process in case we need to go back and see where a certain piece of code originated from.
That's a very good idea. Yeah, fine with me.
We'll certainly squash before we merge, though. So that the history of the master branch is clean.
Okay.
Yeah, the only thing here is, can we do the review on the -devel branch then?
Well, now
the reason why I'm saying yes.
Now the JV, so RISC-V-Devel and RISC-V are now exactly the same.
Yes, they are, but you cannot really put anything into the Eclipse's master branch because all those commits don't have the signed off tagline.
Okay, we can rewrite this. But yeah, this is something I don't still understand.
To just squash, and on the squashed commit put in the sign off by Jan Brani, signed off by Boris Shengarov?
No, we can just add the sign off to every single commit message.
I don't think that's
every
necessary.
single one of these 31 to 35 or so.
If the goal is ultimately to squash everything, then all that squashed one has to be signed at the end.
Yeah.
We'll just ignore the fact that the Eclipse sign-off thing fails until.
Yeah.
I don't think that's a big issue.
And another minor point while you're doing that kind of work is to make sure that the copyrights in all the files are there, and also that the leading date is 2019. So
Okay,
a few that I looked at yesterday, they were all 2018.
Right.
Yeah. Sure.
Is there any third-party code here, or is it all stuff that you wrote?
No, there is no third party. We wrote it completely all ourselves.
Okay, cool, thanks. That's easier. No other CQs needed then, just the one.
Okay, so I'm just putting down notes that, okay, copyright, 2019,
Okay, Boris, I don't know how much time you wanted to have for IL specification. I'm assuming 4 minutes isn't going to do it justice. Do you mind if we move that to the next call, or do you have something that you wanted to ask? Or?
No, not really. We can discuss it whenever we want, or we can organize a call because I'm not sure how many.
Well, we can do it in 2 weeks. That's not a problem.
In 2 weeks, let me see. No, in 2 weeks, that's the week for the RISC-V workshop in Switzerland. Let me verify. So in 2 weeks, we're talking about, the 6th,
okay.
Right?
No,
yeah,
right.
June 6th. June 6th still works, yeah.
Okay.
Yeah.
So either you can quickly give us an introduction now in a few minutes, or maybe we can just hold off until the June the 6th then.
Hold it off.
Okay. All right. Okay. So so we'll look forward to that pull request, and to get that in. I'll also start looking into what we need to do from the infrastructure side in order to be able to get the some sort of testing going for this. I think there's some parallels with the AR64 that we can do. So.
Excellent. If you have any questions about how to set this stuff, just drop me a message. I can help you on.
Absolutely. Thank you.
Aspect.
Great. Okay. Any questions for Boris or Jan? Or do you guys have anything you want to? Anything else you want to talk about there?
I'll just echo your comments from before. It's really great to see this kind of contribution to the project.
Mm-hmm.
So thanks.
Yeah, thank you for your work.
Thanks.
Okay. All right. Well, if there's nothing else, I guess we'll end the call. So thanks everyone for calling in.
Thank you.
Bye.
Thank you. Have a nice day.
Thanks, bye.